Hello, everybody, and today, as part of our series in our course on science, we have taken new guide to science by Isaac Asimov, and we have already covered till early measurements. First chapter, size of the universe, early measurements. The next chapter, or the next subheading, is measuring the solar system. We'll do that now. Measuring the solar system. The mere fact that the sun was placed at the center of the solar system did not in itself help determine the distance of the planets. Copernicus adopted the Greek value for the distance of the moon, but he had no notion of the distance of the sun. It was not until 1650, recently, that a Belgian astronomer, Godfroy Wendelin, Godefroy, Wendelin, Wendelin, repeated Aristarchus's observations with improved instruments and decided that the sun was not 20 times the moon's distance, 5 million miles, but 240 times 60 million miles. 6 crores. The estimate was still too small, but it was much more accurate than before. This is also too small. In 1609, meanwhile, the German astronomer Johannes Kepler had opened the way to accurate distance determination with his discovery that the orbits of the planets were ellipses, not circles. For the first time, it became possible to calculate planetary orbits accurately, and furthermore, to plot a scale map of the solar system, that is, the relative distances and orbit shapes of all the known planets in the system could be plotted. What a wonder! Thus, if the distance between any two planets in the system could be determined in miles, all the other distances could be calculated at once. See the detective work? The distance to the sun, therefore, so it's like a door opening, no? All these concepts. The distance to the sun, therefore, need not be calculated directly, as Aristarchus and Wendelin had attempted to do. The determination of the distance of any matter body, such as Mars or Venus, outside the Earth Moon system would do. One method by which cosmic distances can be calculated involves the use of parallax. Very interesting concept. It is easy to illustrate what this term means. Hold your finger about 3 inches before your eyes. You can do that now. And look at it first with just left eye and then with just the right eye. I just did it with my book. Your finger will shift position against the background, right? Because you have changed your point of view. Now, if you repeat this procedure with your finger farther away, say at arm's length, the finger again will shift against the background, but this time not so much. The amount of shift can be used. Detective work again. To determine the distance of the finger from your eye, the amount of shift, which is called parallax. Of course, for an object 50 feet away, the shift in position from one eye to the other begins to be too small to measure. We need a wider baseline, right? Than just the distance between our two eyes. So if I'm standing here and I'm standing, go there, then I see, then it be better. Further distances, we can see the parallax. But all we have to do to widen the change in point of view is to look at the object from one spot, then move 20 feet to the right and look at it again. Now the parallax is large enough to be measured easily and the distance can be determined. So the distance towards any, suppose your friend is very far away, you can determine the distance very easily. Interesting, no? You stand here, look at him, then go on the right, look at him. There is a parallax, like, you know. Then you put your finger in front of you, check the parallax, and then do the ratio. Right? Interesting. Indirect. So it's not that everything has to be known directly. In fact, most of physics is indirect. In fact, a point comes where you can never know that which is giving rise to something. What about that? Mind blowing, no? Because you can never know light because you see because of light. So how can you see light? That is a naive realism concept for in philosophy and physics. Actually, it's both. That's where the whole philosophy turned, and people may made it mystical for no reason. for no reason. It is just a formulation. It is just a mystery, the acceptance of a certain, not even mystery, the facts of universe. That is why one must study science. Also, uh, yeah, so now the parallax is large enough to be measured easily and the distance can be determined. Surveys make use of just this method for determining the distance across a stream or ravine. That's what we do in civil engineering. The same method precisely can be used to measure the distance to the moon, with the stars playing the role of background. Surveys make the same method precisely can be used to measure the distance to the moon, with the stars playing the role of the background. Got it? Viewed from an observation in California, for instance, the moon will be in one position against the stars. Viewed at the same instant from the from an observatory in England, it will be in a slightly different position. From this change in position and the known distance between the two observations in a straight line through the Earth, the distance of the moon can be calculated. That's how they calculate. Of course, we can, in theory, enlarge the baseline by making observations from observatories at the opposite sides of the Earth also, right? The length of the baseline is then 8,000 miles. The resulting angle of parallax divided by 2 is a geocentric parallax. The shift in position of a heavenly body is measured in degrees or in subunits of a degree, minus minutes and seconds. 1 degree is 1 by 360 of the circuit around the sky. Each degree is split into 60 minutes of arc and each minute into 60 seconds of arc. We know that. A minute of arc is therefore 1 by 360 into 60 or 1 by 21,600 of the circuit of the sky, while a second of arc is 1 by 21,600 into 60 or 1 by 1,296,000 of the circuit of the sky. Using trigonometry, the interrelationship of sides and angles of triangles, Claudius Ptolemy was able to measure the distance of the moon from its parallax, and his result agreed with the earlier figure of Hipparchus. It turned out that the geocentric parallax of the moon is 57 minutes of arc. Parallax. Nearly a full degree. 57 minutes. This much. The shift is about equal to the width of a 25-cent piece as seen at a distance of 5 feet. This is easy enough to measure even with the naked eye. But when it came to measuring the parallax of the sun or a planet, the angles involved were too small. Got it? The only conclusion that could be reached was that the other bodies were much farther than the moon. How much farther? No one could tell. Trigonometry alone, in spite of its refinement by the Arabs during the Middle Ages and by European mathematicians of the 16th century, could not give the answer. But measurement of small angles of parallax became possible with the invention of the telescope. So all this was happening with the naked eye. Telescope changed all that, right? Which Galileo first built and turned to the sky in 16 night after hearing a magnifying tube that had been made some months earlier by a Dutch spectacle maker. The method of parallax passed beyond the moon in 1673, when the Italian-born French astronomer Jean-Dominique Cassini determined the parallax of Mars. He determined the position of Mars against the stars, while on the same evenings, the French astronomer Jean Richer in French Guiana was making the same observation. Combining the two, Cassini obtained his parallax and calculated the scale of the solar system. He arrived at a figure of 86 million miles for the distance of the sun from the earth. 86 million miles. 8.6 crores from the earth. A figure only 7% less than the actual one. Since then, various parallaxes in the solar system have been measured with increasing accuracy. In 1931, a vast international project was made out of the determination of the parallax of a small planetoid named Eros, which at that time approached the Earth more closely than any heavenly body, except the moon. Eros on this occasion showed a large parallax that could be measured with considerable precision, and the scale of the solar system was determined more accurately than ever before. From these calculations, and by the use of methods still more accurate than those involving parallax, the distance of the Sun from the Earth is now known to average approximately 92 million, 9 lakh 65,000 miles, 9.2 crores, give or take 1,000 miles or so. Because the Earth's orbit is elliptical, the actual distance varies from 91 to 94 crores. This average distance is called the astronomical unit. So they found a new astronomical unit to make it more easily to measure. Okay, AU and other distances in the solar system are given in this unit. Saturn, for instance, turned out to be on the average 887 million miles from the Sun, or 9.54 AU. As other planets, as the outer planets, Uranus, Neptune, and Plato were discovered, the boundaries of the solar system were successively enlarged. The extreme diameter of Pluto's orbit is 7,300 million miles, or 79 AU. AU is the distance from Earth to Sun, so like that, relative measurements give a clarity, no? And some comets are known to recede to even greater distances from the Sun. By 1830, the solar system was known to stretch across billions of miles of space, but obviously, this was by no means the full size of the universe. There were still the stars. Billions of miles is the solar system only. Billions of miles is the solar system only. And then there are billions of such stars, galaxies. Wow. That is our universe. Wonder, no? And that completes the chapter. The next chapter is farther stars.